Separable differential equations. Objectives. By the end of this lesson, you should be able to recognize a separable differential equation, separate the variables given a separable differential equation, solve a separable differential equation with or without an initial condition, and understand the application to differential equations in a variety of settings. This lesson has a prerequisite that students have already viewed the lesson on differential equations. Definitions for this lesson. A separable differential equation. A separable differential equation is a differential equation that has the form dy dx equals f of x times g of y, so that it can be rewritten in the form g of y dy equals f of x dx. Explicit and implicit solution. An explicit solution is any solution that is given in the form y equals f of x. In other words, the only place that y shows up is on one side of the equal sign, and is only raised to the first power. An implicit solution is any that is not in explicit form. Steps for solving a differential equation. And you'll notice these are very similar to the steps for solving a differential equation, except for the first and the last step. So the first step, separate the variables by gathering the same variables on opposite sides of the equal sign. So the equation looks like g of y dy equals f of x dx. Then we're going to integrate both sides with respect to their appropriate variable. Again, both indefinite integrals will yield a generic constant, but we only include the plus c on the side of the independent variable, mostly x or t. If provided, we solve for the initial condition. And then finally, we substitute the value of c back in, but this time we need to solve explicitly for the dependent variable, usually y. So now that we have separable differential equations, we're going to have to go an extra step in most cases to solve explicitly to get y on one side by itself. So let's go ahead and look at some examples. Example, solve dy dx equals 6xy squared given the initial condition y of 1 equals 1 over 9. So this looks really similar to the other differential equation problems, except for now we have this variable y. So what we're going to try to do is separate the variables. So get all the terms with x's on one side and y's on the other side. So let's rewrite the problem. Dy dx equals 6xy squared. And I'm going to do this one at a time. So the first thing I'm going to do is multiply both sides by dx, just like in the previous differential equation problems. So now we have dy equals 6xy squared dx. So now on the right side I have all of my x's, but I have this y squared that I don't want to be there. Now since everything here is being multiplied, I can divide by y squared on both sides to get rid of the y squared. So I'm going to rewrite this. The y squareds will cancel. On the left, I'm going to rewrite this as 1 over y squared dy. And on the right, I have 6x dx. And now that we've separated the variables, I have everything to do with y's on one side and everything to do with x's on the other. I can take the antiderivative of both sides. So here, let's go ahead and rewrite this as the integral of y to the negative 2, so I can use the power rule, equals the antiderivative of 6x dx. So the antiderivative on the left side is going to be negative y to the negative 1. Again, we're not going to include the plus c on the side of y. I'm going to instead include the plus c on the side with the x's. So here, using the power rule, I'm going to have an x squared divided by 2. And then 6 divided by 2 is 3, so I'll have 3x squared plus my generic constant c. Alright, and now I need to solve for my constant c using my initial condition. So let's go ahead and solve that off to the side. But first I'm going to rewrite this as negative 1 over y equals 3x squared plus c. So now I'm using this initial condition. When I plug 1 in for x, I get out the y value having to be 1 over 9. So this equation becomes negative 1 over the y value is 1 over 9 equals 3 times 1 squared plus c. So 1 over 9 becomes just 9. And there was a negative in front, so the negative stays there. So negative 9 has to equal 3 plus c. And now if I subtract 3 from both sides, I get negative 12 is my constant c. So now what I can do is go ahead and substitute this value of c back in to my equation. I'm going to go ahead and choose to substitute it back into this version right here, where I've already rewritten y to the negative 1 is 1 over y. So what I have is negative 1 over y equals 3x squared minus 12. Now, the last step is to write this as an explicit equation. So I need to get y by itself on one side. So let me go ahead and multiply both sides by y. So I have negative 1, if I multiply by y, equals y times the quantity 3x squared minus 12. So now if I want to get y by itself, I need to divide both sides by 3x squared minus 12. So now these two terms will cancel because there's multiplication, and I end up with negative 1 over 3x squared minus 12 equals y. As the solution, the particular solution to my original differential equation using the initial condition, y of 1 equals 1 over 9. So you'll notice almost everything stayed the same, except that the first thing we needed to do was isolate the variables, separate them. That's why it's a separable differential equation. And then the last step is to make sure we can write this as an explicitly defined function. In other words, get the y by itself on one side of the equal sign. Okay, let's jump into another example. So now I have dy dx equals negative 2x divided by y. So first step, multiply both sides by dx. So now I have dy equals negative 2x over y dx. So to get rid of the y, I'm going to multiply both sides by y. So I end up with y dy. The y's cancel on the right, equals negative 2x dx. And now that we've isolated the variables, the dy and y is on one side, the x dx is on the other, I can integrate both sides. The left side will become y squared over 2. The right side will become negative x squared plus c. In this case, I do have an initial condition. So whenever I plug x equals 1 into the equation, I should get out a negative 1 for the y value. So here, let's go ahead and solve for it up at the top. I'm going to end up with a negative 1 for the y squared over 2 equals negative, my x value is positive 1 squared plus c. So negative 1 squared is positive 1 over 2 equals negative 1 plus c. If I add 1, I'm going to get 1/2 plus 1, so that's 3 over 2 equals c. So now I can substitute this constant back in to the general equation. So I end up with y squared over 2 equals negative x squared plus 3 over 2. And now the last step is to get y by itself. So let's go ahead and multiply both sides by 2. So now I end up with y squared equals, I'm going to distribute this 2 in, so I'll get negative 2x squared plus 3. So now to get the y by itself, I need to take the square root of both sides. So I'll end up with y equals the square root of, I'm going to rewrite this as 3 minus 2x squared. But something unique happens when I take the square root of a square. I get out a plus and a minus. So I can't have both be a specific solution because this is two different solutions. And this is where it takes a little bit of thinking going back to my initial condition. My initial condition told me that when I substituted a 1 in for x, I got out a negative 1. So if I look at what I'm about to say is my specific solution, I should be able to plug in an x value of 1 in and get out a negative 1. So if I plug in a 1 here, I'm going to get 1 squared is 1, times 2 is 2, 3 minus 2 is positive 1. Now if I choose the positive option here, then I'm going to end up with positive 1 as the output, but I need a negative 1. So that means that I ignore the positive option, and I can only choose negative the square root of 3 minus 2x squared. So the negative square root option is my final solution. So again, I cannot have plus and minus be a specific solution. I need to choose one or the other, but I need to reference my initial condition in order to make that decision. Solve dy dx equals x to the fourth times the quantity y minus 2 given y of 0 equals 0. So let's try to separate the variables. So we have dy dx equals x to the fourth times y minus 2. So again, first step, multiply both sides by dx. Dx's cancel. I end up with dy equals x to the fourth times y minus 2 dx. So I want to get rid of the term with y minus 2. And since everything's being multiplied and this is one whole term, I can go ahead and divide both sides by the term y minus 2. So these cancel, and I get dy over y minus 2 equals x to the fourth dx. Alright, so now I take the antiderivative of both sides. The antiderivative on the left should look familiar. We write the antiderivative of dy over y minus 2 as the natural log of the absolute value of y minus 2. And on the right, we'll get 1/5 x to the fifth power plus c. So now let's go ahead and try to solve for the initial condition. So whenever I substitute in 0 for x, I get out a 0 for y. So the natural log of the absolute value of 0 minus 2 has to equal 1 over 5 times 0 to the fifth plus c. So natural log of absolute value of negative 2. Well, the absolute value makes the negative 2 positive, so the left side is just natural log of 2, and the right side is c. So my c value is natural log of 2. So let's substitute that back in. Natural log of y minus 2 in absolute value bars equals 1/5 x to the fifth plus the natural log of 2. So now the tricky thing is going to be solving for y, rewriting y as an explicit function. So we want to somehow get this y minus 2 out of the natural log function, and then we're going to have to worry about getting it out of the absolute value bars. So first things first is getting rid of the y minus 2 being inside a natural log function. So I need to think the inverse of natural log, which is the exponential function. So I need to exponentiate both sides. So this up here was the scratch work for finding the constant c. And up here we will go ahead and continue the problem. So I need to exponentiate both sides, so it's going to be e to the natural log of the absolute value of y minus 2. And then do the same on the right side, e to the 1 over 5 x to the fifth plus the natural log of 2. Now on the left, we did that because e and natural log are inverses, and they cancel, and what's left over is the absolute value of y minus 2 equals e to the 1 over 5 x to the 5th plus natural log of 2, all up in the exponent. So now here's the question. What do we do with these absolute value bars? We can't just get rid of them. That doesn't work. So here's what I want to remind you of for a second. The absolute value function, absolute value of x, is really a piecewise function. So it's the function x when x is when x is greater than or equal to 0. So whenever x is a positive number or 0, the absolute value function does nothing to it. But whenever x is less than 0, then the absolute value bars make the number negative positive by really putting another negative in front of it. So if we plug negative 2 into the absolute value function, we get out positive 2. But another way to get out a positive when you have a negative number is to multiply by a negative. So this is the formal way to define the absolute value function. So now here, let's think about the absolute value of y minus 2. I can rewrite that as a piecewise function. So it's the piecewise function, just y minus 2, whenever the y values I plug in are greater than or equal to 2. So whenever I plug something in for y that's bigger than 2, so let's say 5. 5 minus 2 is 3. Nothing happens. This does nothing with the absolute value bars. I still end up with positive 3. It's only when I start plugging in values for y that are less than 2 that I have to start making those values positive no matter what. Well, that's the same as putting a negative in front of the function. Negative y minus 2. Just like over here, we put a negative in front of the x. So why am I even doing all this? Because I have to think about this absolute value function as a piecewise function because I have to reference the initial condition. I want the specific piecewise, or the specific function that will yield whenever I plug in a 0, I get out a 0. So here, the absolute value of y minus 2 is two different pieces of a function. I'm concerned with the one that's defined where 0 is defined. So this bottom piece, well, 0 is less than 2, so I'm looking at the bottom piece of this piecewise function. So the absolute value of y minus 2, if we erase this part, is negative the quantity y minus 2. So this was a lot of a pre-calculus review here, just to decide what to do with the absolute value. But the point is we can't take it away. So it's either going to be just y minus 2, like we did just take away the absolute value bars, or it's going to be its opposite. So you put a negative in front of it. And in this case, it's going to be the opposite. So now we can just continue to erase this. We're done with that. And negative the quantity y minus 2 has to equal e to the 1 over 5 x to the 5th plus natural log of 2. So now it's a matter of multiplying by the negative. So we get y minus 2 equals negative e to the 1 over 5 x to the 5th plus natural log of 2. And then adding the 2 to the other side. So y finally, explicitly defined, is 2 minus e to the 1 over 5 x to the 5th plus the natural log of 2. And this is our final answer. So now we've gone over a few examples. One involved getting a plus or minus out with the square root function, and now this is handling what happens when we end up with an absolute value function. Now let's go over one more example that looks a little bit different. So now we have solve y prime equals e to the x plus y equals 0. So now this may not look like a differential equation, but it's an equation that involves a derivative. So the question is, how do we separate the variables? So let's go ahead and start by rewriting y prime as dy dx. So we have dy dx plus e to the x plus y equals 0. Well, we're used to having dy dx equals something, so let's go ahead and subtract e to the x plus y to the other side. So we have dy dx equals negative e to the x plus y. And now we're trying to make sure that we end up with all of the x's on one side and the y's on the other. But here, this e to the x plus y, well, right now, that's one whole term that can't be separated. So I have to use my properties of exponents to rewrite this as negative e to the x times e to the y. So remember, I can split these up using my properties of exponents. As long as they have the same base, I would add their exponent. So similarly, I can split them back up into their own exponential functions. So the right side is negative e to the x times e to the y, and the left is my dy dx. So now I can separate the variables by multiplying both sides by dx. So dy equals negative e to the x, e to the y dx. And then the last step would be to divide by e to the y on both sides. So on the left, I end up with e to the negative y dy, and on the right, I have negative e to the x dx. And I'm integrating both sides at this point since I've separated the variables. So now on the left, the antiderivative is negative e to the negative y, and on the right, the antiderivative is just negative e to the x plus c. So now the last step is going to be to write this explicitly in terms of y. So notice there was no initial condition, so I don't have to worry about solving for the c, but if possible, I still want to write y as an explicit function of x. So let's continue the problem up here. The next thing I'm going to do is divide both sides by the negative. So I'm going to have e to the negative y equals, this negative will become a positive, e to the x. And now if I want to, I can write minus c. But really that doesn't matter because c is a generic constant anyway. So plus c, minus c, it's all the same thing. So if I want to go ahead and carry that negative to the c, I can. Or I can leave it a plus. It doesn't really matter. Alright, so now I'm going to make sure I can get the y out of the exponent. So how I'm going to do that is take the natural log of both sides. So I'm going to use the inverse property again of the relationship between natural log and e. So natural log e to the negative y equals natural log of the quantity e to the x minus c. And now the natural log and e cancel, so I end up with negative y equals natural log of the quantity e to the x minus c. And then the last step is to divide both sides by the negative, so negative natural log of e to the x minus c. Now real quick, on this step to this step here, a lot of students might be inclined to cancel the natural log and the e right here because of the inverse property, but I cannot do that because of this minus c or plus c if you left it as a plus. So the only way I can do that is if I have exactly natural log right next to e to the x, and that's it. So there's nothing I can do with natural log of an entire quantity of a difference of two things. There's no simplifying I can do at that point. So the most simplified answer I can get is down here, with y equals negative natural log of e to the x plus c or minus c. Again, that is the only sign here. That's irrelevant. That doesn't matter. And now finally an application problem. So this is the 2012 AB/BC free response question number 5. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at time t days after it is first weighed, then db dt equals 1 over 5 times 100 minus b. Let y equal b of t be the solution to the differential equation above with initial condition b of 0 equals 20. Part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. So this is a bit of a loaded question. What's happening is they're telling us about how fast a baby bird is growing. So when we see dB dt, we're thinking a rate of change because we've been given a derivative or an instantaneous rate of change. So the rate at which the bird is growing is given by 1 over 5 100 minus b, where b is itself a function, and it's the function of the weight of the bird t days after the very first time it is weighed. So on day 0, when the bird is first weighed, it's 20 grams, and from then on, to figure out how much it weighs, you'd have to plug the number of days into this b function that we don't have yet to figure out how much it weighs. But how fast it's growing is given by this equation, this rate of change, or this derivative. So there's a lot of information given here. The last part tells you the solution to the differential equation, a specific solution, has an initial condition, b of 0 equals 20. Well, they didn't really explicitly need to give you this. They in fact already gave it to you in this sentence here. At time 0, when the bird is first weighed, its weight is 20 grams. So if b of t is the weight of the bird in grams, when you plug in t equals 0, you get out 20. So this was just their nice way of telling you exactly what they gave you in mathematical notation, so you wouldn't have to figure it out from this sentence, but it was already given. Now, part A. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So they're not asking you about when the bird weighed 40 grams or when it weighed 70 grams. They're asking you, is the bird gaining weight faster? So when you see this word faster, you should think rate. And when you think rate, you think derivative. So for part A, we need to substitute in 40 grams into B to find the rate at which the bird was gaining weight when the weight was 40 grams. So B of t is weight. So for part A, we're solving dB dt when B equals 40. So if I go ahead and substitute 40 in, I get 1 over 5 times 100 minus 40, or 1 over 5 times 60, which is 12. Now, the rate of change, how fast the bird is gaining weight when the bird is 40 grams, is at a rate of 12 grams per day, right? That would be the units here. So the bird is gaining weight at a rate of 12 grams per day. So when the bird weighs 70 grams, now we're plugging in, or we're solving dB dt when b is 70. So we have 1 over 5, 100 minus 70. So 1 over 5 times 30, or 6 grams a day. So the question is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So when the bird weighs 40 grams, it's gaining 12 grams a day. When it weighs 70 grams, it's gaining 6 grams a day. So the answer here is when the bird weighs 40 grams, the bird's gaining weight faster because this value of 12 is greater than this value of 6. So that would be your reasoning. Since dB dt when b is 40 is greater than dB dt when b is 70, that means that when the bird weighs 40 grams, it's gaining weight faster than when the bird weighs 70 grams. So that is the answer to part A. Let's move on to part B. Find the second derivative of b with respect to time in terms of b. Use the second derivative to explain why the graph of b cannot resemble the following graph. So what do we have? We have dB dt equals 1/5 times 100 minus b, and we're asked to find the second derivative. So we need to take the derivative of the derivative. So let's rewrite it. We have dB dt equals, I'm going to go and distribute this 1 over 5 in. So dB dt is 20 minus 1/5 b. Alright, so the second derivative is going to be, the derivative of 20 is 0. The derivative of negative 1/5 b is negative 1/5. Now I'm taking the derivative with respect to time. B is not the same as t, so that means this is implicit differentiation. So the derivative is negative 1/5 dB dt. So now, what did it tell us to do? Find the second derivative in terms of b. Well, this is not in terms of b. This has a dB dt in it. But dB dt is 1/5 times 100 minus b. So I have negative 1/5 times, I'm just going to substitute dB dt in, 1/5 times 100 minus b. So let's simplify this. I get negative 1/25 times 100 minus b. And that's my second derivative in terms of the function b. So we've answered the first part of the question. Find the second derivative in terms of b. Now, use the second derivative to explain why the graph of b cannot resemble the graph below. So this graph here, we want to say that this function, or this second derivative of the function b, doesn't match up. Well, what do we know about second derivatives? If a second derivative of a function is negative, then the original function is concave down. Well, let's take a look at this. Here, well, the baby bird's weight has to be greater than 20 because the very first time we measured it, the baby bird's weight was 20 grams. So if I start to plug in 20 in for this b, well, 100 minus 20, that's going to give me a positive quantity, but times a negative will give me a negative. So for this entire graph here, I know that the second derivative has to be negative. Well, if the second derivative is negative, the original function must be concave down. Well, this graph I see here starts out as concave up, and only about right here switches to a graph that's concave down. So we would write, since the second derivative, so d2b over dt squared, is less than 0, b must be concave down. Not shown in the graph given. So the wording doesn't have to be exact, but some reference to that the second derivative is negative, forcing the original function to be concave down, is the argument as to why this graph shown is not the graph of the original function b that tells about the baby bird's weight at any particular time. So parts A and B are done. Part C is going to be the long part. Part C is going to be the part where we actually use separation of variables and solve the differential equation for the original function b. So part C, use separation of variables to find y equals b of t, the particular solution to the differential equation with initial condition b of 0 equals 20. So let's rewrite for ourselves the differential equation. DB dt equals, it was 1/5 times 100 minus b. Alright, so this was our original differential equation. So let's go ahead and solve this. I want to get everything to do with b's on one side and everything to do with t's on one side. So let's multiply both sides by dt. So dB equals 1/5 times 100 minus b dt. Now divide both sides by 100 minus b. So the 100 minus b's cancel. I get dB equals 100 minus b equals 1/5 dt. I can integrate each of these sides. The left side is going to be some form of the natural log, but this negative in front of the b is going to give me negative the natural log of 100 minus b equals, the antiderivative of 1/5 dt is just 1/5 t plus c. So now I need to go ahead and try to use the initial condition. So the initial condition says when I plug in t equals 0, I get out b equals 20. So let's solve for the initial condition off to the side. I'll get negative natural log of 100 minus 20 equals 1 over 5 times 0 plus c. So c is negative the natural log of 80. So I have negative the natural log of the absolute value of 100 minus b equals 1 over 5t minus the natural log of 80. And now we need to solve for b. So let's divide both sides by the negative. We get positive natural log of 100 minus b equals negative 1/5 t plus natural log of 80. And we exponentiate both sides. The e to the natural log cancels. I get 100 in absolute value bars minus b equals e to the negative 1/5 t plus natural log of 80. And then similarly with the absolute value problem, I need to make a decision on which to use. And because I'm concerned with plugging in 0, if I plug in 0 for b, I'm going to get positive 100. So there's nothing wrong with just removing the absolute value bars. So this would be 100 minus b equals e to the negative 1/5 t, be careful with the t, plus natural log of 180, or 80. And then if I subtract 100 and divide by the negative, I'm going to get negative b equals negative 100 plus e to the negative 1 over 5t plus natural log of 80. Or b equals 100 minus e to the negative 1 over 5t plus natural log of 80. And that is my final answer.